Okay, David Gish here. I want to go through a little overview of Chapter 5 in statistics, and this is about probability distributions. So we want to take what we learned in Chapters 1 through 3, where we eventually made a frequency table, and then we said, hey, where is the center, what is the spread, all of that, and then we want to combine that with probability. All right, so that is our idea, that is our goal here. So we'll talk about probability distributions, what are they? Then we'll talk about the binomial probability distribution, and then also parameters for these. So like your mean and standard deviation. Now, there is another section some instructors may cover. Typically you won't though, but there are lots of other types of probability distributions, and so one other example that is included in this textbook that we use is the Poisson distribution, and we're not going to do that, but there's Poisson, geometric, tons of them. So anyhow, we're just going to focus on the basics here. So anyhow, what is a probability distribution? Well, it's where we create basically a frequency table and we give a probability for each value. And that's it. And then we can then do the same old stuff as before. What's the center? What's the spread? And then what is unusual and all that. All right. So first of all, to have a probability distribution, we need to define what is a random variable. So a random variable is just some numerical value associated with each outcome. So it's got to be something you can quantify numerically. And then we usually denote it by X. And an example, the number of sales calls a person makes in one day, maybe the hours spent on a sales call in one day. Those are examples of random variables. All right. There are two types of random variables. One is discrete, where they're separate. You can count them. An example is those sales calls, right? You either make 0, 1, 2, 3. You don't make 4.5 sales calls in a day. Either you make the call or you don't, right? So that's a discrete random variable. As opposed to a continuous random variable, like the hours you spend. Now you could measure that down to a decimal value. So think of discrete as no decimals, continuous, you could have decimals, all right? Now Chapter 5 focuses on discrete, and then Chapter 6 will talk about continuous. All right, so discrete probability distributions. Well, first of all, it's a probability. So every probability should have a value between 0 and 1. And then all these probabilities, when you add them up, they should add up to 1. So it's discrete, they're separate, so there's no overlap or anything like that. So if you add up all these individual values, they should add up to 1. So here's an example. We took a survey, a passive-aggressive survey of 150 employees, and on the score, your random variable is the score in the exam, and it could be 1 through 5. I think 5 is, most aggressive, 1 would be most passive. And then here's your results over here, right? So we've summarized the results in a frequency table. And now if you find the probabilities for each of these, so probability for scoring a 1, 24 out of 150, etc., etc. Put it together, and then here you go. This is a discrete probability distribution. Discrete because the scores are separate, 1, 2, 3, 4, 5. And then here we go. Here's our probabilities. Each of them is between 0 and 1. And if you were to add them all up, they would add up to 1. So there you go. That's it. And now some of you may have noticed, but this probability, that's just relative frequency. That's the frequency over n, right? So nothing fancy there. Another example, if you look at the sum of 2 die, when you're rolling 2 die in a board game, let's say, here are all those probabilities in fraction form, right? And so this is also a discrete probability distribution. So the sum could be 2. That's if you rolled 2 1s. It could be up to 12 if you rolled 2 6s, and everything in between. And then here we just did the probability as fractions instead of decimals, but that's fine. And then of course, so this is essentially a frequency table where probability is relative frequency. And then, of course, just like in chapter 2, you could then take this and then you could turn this into a histogram. And so here it is, and then the axis is probability, or in other words, relative frequency. So all that stuff is just the same as we did before. It's just we're thinking about it kind of in a special way now. Okay? And now, here's where it gets a little tricky. Remember, it's got to count something. So imagine if I flipped a coin, flipped 2 coins, right? Now, we might, in chapter 4, think of it like this. I could get 2 tails, a tails on the first coin, a heads on the other one, or vice versa, or I could get 2 heads, right? But in a probability distribution, you have to count something. So rather than thinking of it like this, I need to think about, what do I want to count? Well, I have 2 choices. I could count the number of heads, or I could count the number of tails. So I chose the number of heads. And so then the number of heads could be 0 heads, 1 heads, or 2 heads. And then here are the probabilities for those. So a lot of scenarios where, by the way, heads and tails, that's not numerical, right? So at first it seems like the outcomes are not quantitative and all that, but you could still count them and get these quantities here, okay? So we can turn lots of things into discrete probability distributions and count them, even though it's not quantitative data to start with. But there's a nice example of that, so just keep that in mind. All right, now, once I have that, you can actually find the mean, the variance, and the standard deviation. So we just showed you back here, right? We could create a frequency table, essentially, right? We could turn it into a histogram. Great. So we can view the shape, right? We can say, hey, here's roughly the center. I could tell if it's skewed, this and that. But then to really pin it down, we say, hey, I want to know, what is the mean? What is the standard deviation? And go a step further. There it is. And so these are the formulas for that. Now, keep in mind, this is a formula. It's given for the context of dealing with a probability distribution. However, mathematically speaking, it's actually the same thing as a weighted mean. We learned weighted means back in chapter 3. Yeah. So it's really kind of the same thing. But anyhow, here's the formulas for these. Now, let's just go through some of these real quick. So if I had that passive-aggressive survey, here's the scores, here's the probabilities. So the mean is the sum of x times p of x. So p of x being the probability. So here I go. Here's x times p of x. Here's x times p of x, x times p of x, x times p of x, x times p of x. Add them all up, sum them up. So if I sum this column, I get roughly 2.94 or 2.9. So there you go. That is the mean. So in other words, on average, these employees scored roughly on average a score of 2.9. All right. So nice. Now we could take it a step further. We could find the variance. We could find the standard deviation. If you do this by hand, which you shouldn't, but if you did, you should really make a chart to organize this, and it would look something like this. So remember, the mean's 2.94. So just like when you did standard deviation before, this is a deviation, x minus the mean. How far from the mean are you? I got some positives and negatives. Just like before, you square them to make them all positive, right? And then now we actually take it times the probability. So I'll take this number times the probability, and then I get a bunch of these, and then the formula says, hey, add all those up. So add all those up. In other words, add up this column now. That gets you the variance, and then if you wanted the standard deviation, you take the square root of that. There you go. So roughly spread out 1.271 on average around that mean. Okay? So there's your variance and standard deviation. Now, don't do this by hand. Nobody does this by hand. So many calculations, so easy to make errors. So use StatCrunch. So in StatCrunch, type the data in columns. So here's my X, 1, 2, 3, 4, 5. Here's my probabilities. I typed them in. And then you can go to Stat, Calculators, Custom. Okay. Now, calculators you should think of in StatCrunch as distributions, and every probability distribution is custom to its probabilities. So that's a way you can think of, oh, why is it custom? Because it's custom to its unique probabilities. So anyhow, you click on that, and then you tell it to, this is the columns for the variable, here are the weights, if you will, and then it spits it out, and it tells you right on the screen, then here's the mean, here's the standard deviation. So it'll calculate that automatically in StatCrunch. So don't do that by hand. That's just kind of ridiculous, honestly. So that is one type of discrete probability. This is just if you gather data, you could turn it into that, and you're good to go. Now there's a special type of discrete probability distributions, and that is binomial probability distributions. And so binomial is when you're doing something a fixed number of times, and each trial is independent, right? So each trial has no effect on the other. Okay? And there's only two possible outcomes. Either this happened or it did not. So something, you either have a success or a failure. And we denote the probability of success as a P of S, and the probability of failure, P of F. Now our special notation, N is the number of trials in the experiment. Lowercase p is the probability of success in a single trial. Lowercase q is the probability of a failure, and these are opposites, right? Because you either have a success or you don't. And then x is your random variable. It's the number of possible successes. So if I have n trials, if I try something n times, I could have 0 successes, 1 success, 2 success, 3 success, all the way up to n number of successes. So, for example, here we go. Let's identify the variables for this. So I have a certain surgical procedure, has an 85% chance of success. A doctor performs the procedure on 8 patients. The random variable represents the number of successful surgeries. So n is 8, that's the number of trials. Probability of success is 0.85, so just writing that as a decimal. So probability of failing, opposite of that, is 0.15. And x would be, well, if they did this 8 times, you could have 0 successes, 1, 2, 3, 4, 5, 6, 7, or 8 successes, right? So there you go. There's all your variables. Now, if I put this all together, I can create a probability distribution. But to do that, I need to know the probabilities. And here is the formula for the binomial probability. And so P of x, x is the number of successes you care about. And again, lowercase p, q, and all that stuff's the same as the last slide in terms of what they mean. Now this, if you recall from chapter 4, this is special notation for combinations. So this means if I do something n times, how many ways can I have x number of successes? Okay, so that's that notation there. So this is a combination. Okay. So, for example, going back to that knee surgery, let's say I perform this 3 times instead of 8. So 3 times now. What's the probability of exactly 2 successes? So x would be 2. There's n is 3 surgeries, choose 2, so this is a combination. P is 0.85. I want 2 successes, therefore 3 minus 2. That's 1 failure. This is the probability of failure. So if I multiply all this out, I get 0.325. Okay? So there you go. So that's a probability, a binomial probability. Now, I could do this and for every variable. So for 0, 1, 2, and 3. And when I get all those probabilities, I could put a chart, and that creates a binomial probability distribution. So my discrete variable is the number of successes in 3 trials. And then here's the probabilities for each of those, calculated using the binomial probability formula. And now I have a binomial probability distribution. So that's pretty neat. Now, just like with the discrete ones, you can use StatCrunch to do this for you. And in fact, because this is all based on this formula, right? So this is kind of theoretical. You can do this in StatCrunch. So stat calculators, again, calculators are distributions. Click on binomial. And so if we go back, or actually let's not go back, let's do another example. So you take a multiple choice quiz with 20 questions. So that's like 20 trials. Every question has 4 choices. And so, by the way, the probability of a success is you get that 1 out of 4 correct, right? 0.25. A failure, there's 3 ways out of 4 to fail. So 0.75. And so my question is, what is the probability if you were to guess on every question, you get exactly 18 correct? Well, if I was using the formula, 20 is n, 18 is x, crank it out, really, really small. Oh man, no chance. You're not going to guess 18 correct. Now, if you go to StatCrunch, go stat, calculators, binomial, you put in n for 20, you put in p for 0.25. By the way, you don't need to tell it q because p and q are opposites. So if you tell it p, it knows q. And here I put in 18, and then when you hit compute, it makes a nice distribution for you so you can see what's going on here. Also spits out the probability. Now be careful, you notice there's an E here, so that's scientific notation. So this means 1.5552 times 10 to the negative 9th power. All right, which is this number up here if I rounded to 1/6, right? So yeah, so you don't need to go through and calculate all these out and everything. StatCrunch does it. So these heights represent all those probabilities. They're all calculated out here, and then if you just type in whichever one you want to know, it'll spit it out. Okay. Now another nice thing about this is, what if I tweak this question a little bit? So what's the probability you got at least 15 correct? So that's like saying I got 15 or 16 or 17 or 18 or 19 or 20 correct, right? Now we know from chapter 4 that's or, and you would add those up, which means I'd have to calculate each of those separately, and that's kind of a pain because this is just calculating one of them. And so I would calculate doing this with 15, then 16, then 17, then 18, right? Add them all up, that would give you my answer. But again, in StatCrunch, it'll do all this for you. So again, put in n, p, and now you can make this greater than or equal symbol, which means at least, right? At least 15, and it actually does it all for you on the fly. So very, very powerful, very helpful. So use this calculator. We care more about, can you get an answer, can you interpret an answer, can you make meaning of it, than can you do arithmetic. So at least I do. Now your professor may vary on that, and of course if your professor has different instructions, of course follow their instructions. Alright. One last thing I want to know about the binomial probability distribution is the binomial probability distribution kind of changes its shape based on p. Sort of. We'll come back to this later. But here's when n is 10 for all 3 examples. So if p is really low, you notice it kind of clumps around on the low end and then tapers off to the right. So it's a little bit skew right. If p is 0.5, then it's nice and symmetric in the middle, which makes sense. It's half and half. And if p is large, 0.8, and then it clumps around in the high end and it tapers off and it's skew left. So if you know what p is, you can kind of guess if this thing's going to be skewed one way or the other, possibly. All right. So that's something to note. So there is no one binomial probability distribution. It changes shape based on p, but also changes shape based on n. All right, and we'll revisit that later. Okay, so that's something else to note for you. Now, just like with discrete probability distributions, we can find the mean, variance, and standard deviation once again Again, that's our goal. We want to create these distributions so we can see the shape, see what's going on, see if I have outliers, all those kinds of things. But we also want to know, where's the center? What is the spread? That's what we always want to know. And the formulas are really easy for binomial. So the mean is just n times p. Variance is npq. And the standard deviation is the square root of npq. All right. So one last example here. So Pittsburgh, Pennsylvania. About 56% of the days in a year are cloudy. Find the mean, variance, and standard deviation for the number of cloudy days during the month of June. And then let's interpret this and see if there's any unusual values. So n times p, by the way, in June there are 30 days? So you would take 0.56 times 30. That would say, hey, roughly 16.8 cloudy days on average. NPQ would give you 0.74 for the variance, and then you take the square root of that, and there's your standard deviation. So, in other words, this is binomial, by the way, because either you're cloudy or you're not, right? So that's why it's binomial. And one day has no effect on the other. All right, so it's independent. So there you go. Anyhow, on average, there's 16.8 cloudy days within the month of June. That's what this tells us. Oh, by the way, there's your N, P, and Q. Yep. The standard deviation is about 2.7 days. So on average, right, the spread around that, it's not going to be exactly 16.8, but spread about 2.7 around that. Now, remember, when you have standard deviation, we have that bracket of usual and unusual, right? And so if I take the mean minus 2 times the standard deviation, that gives me 11.4. And if I take the mean plus 2 times the standard deviation, that gives me 22.2. So a June with 11 cloudy days or less would be considered unusual because it falls below that. And a June day with 23 cloudy days or more would be unusual. So we can tie this back into chapter 3 and how we kind of determine outliers and all that. So again, that's kind of the power here and some of the things we want to do. So there you go. That's an overview of chapter 5. A lot of stuff there, but just hopefully that helps. Also, use StatCrunch. It's there for you and makes your life so much easier. So don't try to crank all these out by hand. Again, use StatCrunch. The more important thing is, can you take what StatCrunch tells you and then interpret and use it? So like here, I interpreted the results and used those results. Okay, that's more. This is more valuable to me, and in terms of what we want to be able to do with data than just, hey, can you calculate that? All right. Okay, hope that helped. Enjoy chapter 5.